Okay, let me look at a calendar while we do this. So right now, your test is supposed to be on the 20th, and I think that that's going to be fine because we have 3 classes until then, and I think we can do all of this. So let's say your homework 2 is due Friday the 13th. I will grade it over the weekend and give it to you Monday. I would say, I think you could probably turn in your homework 3 on Monday the 16th, but let's just push it to Tuesday the 17th so you can ask me questions on Monday the 16th. Okay, I'm going to write this down. So, homework 2 due this Friday the 13th. Homework 3 is going to be due Tuesday the 17th. I will grade those, and you can pick them up Thursday from Rachel so you can have feedback. Sound good? If you email them to me, I will email you your feedback. Okay. That's a Tuesday. And then on that Friday, when you come in for your exam, you're just going to bring your homework 4 with you. It's a half assignment. It's just 5 questions. Okay. Okay, I think all of that will work. Okay. Any questions for me about any of that? Okay. Ready to do it? Yes. What page are we on? 16? Okay. So now we're going to combine the last 2 things that we've done. So we talked about quantification. We also talked about predicates. So we're going to put those things together now. So like x, q of x, or p of 2, or whatever, wherever we talked about that is that, goodness gracious, it's hard for me to look at that. These are, so like p of 2 is greater than 3. That becomes true or false, whatever. What we're going to do now is add quantification to that. So you could say for all x greater than 2, p of x. So we're going to like combine these ideas. We're going to quantify these predicates, and that's how it's going to go. It's, relatively straightforward, just smishing those 2 ideas together. So let's suppose that I've accidentally convinced myself that for every x in R, x is less than 0. And you want to convince me that I'm wrong. How would you tell me that I'm wrong? Politely is how you would do it. What evidence would you provide? Yeah, you would say, well, Dr. Chalmers, consider x equals 1. Notice that 1 is not less than 0, so you're wrong. Oh, also we're negating them. It's fine. This is fine. We can do this. P is the predicate x is greater than 0. Write this statement symbolically that for all x in R, x is greater than 0, and then do its negation. Greater than 0, yes. So for the statement itself, you would say for all x that are elements in R, x is greater than 0. Yo, have we done this? Have we negated these things yet or not? Yes, we did. No, that's page 16 that we're on right now. This is a problem. I've prepped this, but I also don't know the flow of the new notes. So I don't know when we did it or if I've just done it already because I prepped it already. This is confusing. I don't like this. Okay. Well, whatever. How would you know that that is not true? like this is how you negate a statement, is you give the time when it would not be true. So if I say something like for all x and r, x is greater than 0, how do you negate that?
There exists.
Yes.
X that is not greater than 0.
How could you say that better? Yeah, less than or equal to. This is the backwards of what we actually just did, so that's kind of confusing, but perhaps I should change that in my notes. Like with p's or whatever, this would be for all x in r p of x. The negation would be that there exists an x in r where not p of x. Okay, so let's say that now I have I've been silly, I've confused myself and convinced myself again that there's a real number x such that x squared is equal to -1. Again, so I have convinced myself that there is a real number x where x squared is equal to -1. Suppose again that you want to convince me that I'm wrong. What's your burden of proof? How would you prove it to me? How would you prove to me? Let's pause. Let's write this in symbols, and then we'll talk about what the burden of proof means. So let's put this in symbols. So there is a real number x in R such that x squared is equal to -1. That negation would look like what? Or think about this, let's not think about the negation, but think about the statement itself, that there exists an x in R where x squared is equal to -1. What am I claiming there? What am I claiming with the original statement? Yeah, that there is at least one number where when I square it, I get -1, right? Now, how would you prove me wrong? Your burden of proof, it's a burden now. What is the burden of proof?
It's false for every x.
Yeah, that it would be false for every single x, because I'm saying it's true for one. To prove me wrong, you would need to show me that I'm wrong for every single possible x, right? So the negation here is for all x in R. That thing is not true. So x squared does not equal -1. That's a much more difficult thing to do than this, right? So 4.1 is going to be a lot of this. You're going to disprove statements by finding a counterexample. 4.2 is going to be more of proving statements. That's called, direct proofs. We'll get there. These things are what we just talked about in specific examples. Here they are in general terms. This is hard for me to look at, so. But this is the idea. If this is your statement, then its negation becomes, the negation of a for all statement becomes a there exists statement, where the thing is not true. And then conversely, this statement is that there exists an x in R where p of x is true. The negation is that for all x in R, it's not true. And that's what these things say in more symbols. The negation of for all x, p of x is that there exists an x where not p of x. And then the negation of it there exists where p of x is true is that for all x it's not true. The domain's given there, so that's all of that. Okay, we're going to negate these things with the idea that we don't have the universal set here, the domain written down, but we're just going to do it anyway. So how do I negate this? Number one, it says for all x, x is greater than 3. What would the negation look like?
There exists an x. X is less than 3.
Good. How about for number 2? First things first, we want to switch that there exists to for all, right? Okay. So for all x, how do we negate an and statement? We make it an or. We negate the pieces and make it an or, right? So x is not prime, or x is not even. We're doing okay with that? Yeah? Any questions or comments so far? No? Good to go? I want to negate the statement that all cars are red. Good. For all x and n, that's the natural numbers. For all x and n, x squared plus x plus 41 is prime.
Exists. X squared plus x plus 41 is not.
Good.
Functions such that f is not continuous.
Nope. Careful.
It's the other way around.
Well, so don't worry about that right now. We've got that there exists, oh my word, what in the world? There exists a function f where if f is continuous, then not differentiable. How do you, so we negated this part, right? We made it for all, that's good. How do we negate this part? What's the negation of an if-then statement? No. What's the negation of an if-then statement? When is the only way to show me that a conditional is not true?
Instead of saying f, you say that it is true.
Yeah, it's that the P part happens and the Q part does not happen. Right?
Then f is different.
Right. So how would this actually go with the whole thing here? For all functions f, you did it again. Still made an if-then statement. You still made it an if-then statement.
Okay, where f is continuous and
Yeah.
f is different.
For all functions f, they are continuous and differentiable. That's weird and it's uncomfortable, right? It also reads weird, but that's right. Okay. So this is, saying what we do. We're going to replace each for all with a there exists, replace each there exists with a for all, and negate the p of x, whatever that is. Okay, so we're going to negate these, still going. We're just still practicing. And then we're still going to practice some more. It's a lot of practice, but we can do it, right? Right. So we're going to negate these things. We're making sure we know that we're negating them. Negating that for all n in the natural numbers, there exists an m in the natural numbers where m is less than n.
There exists an n in n. There always is an m in n, where n is less than or equal to n. M is less than or m is greater than or equal to n.
Yeah. Yes. There exists an n in n such that for all m and n, m is greater than or equal to n. All right, how about number 2? Here you got another opportunity to correct negating an if-then statement. The integers. Uh-huh. Good. Good. Any questions about that one? All right, number 3. For all positive real numbers x, there exists a real number y such that y squared equals x. The negation of that?
There exists.
X, and we're gonna positive real numbers, y'all, is r plus. Or you can do r greater than 0. If it was non-negative, you could do this to include the 0. Your book calls that r non-neg. But r plus does not include 0, so just be aware of that. Okay, so for all positive real numbers x, so we have there exists a positive real number x such that for all real numbers y, that's not a y, my bad, y squared does not equal x. There exists a positive real number x such that for all real numbers y, y squared cannot equal x. Is that true? We're not supposed to worry about the true or falseness of the thing. It even says that. It's warm in here, right? It got hot.
Are we supposed to worry about the true or falseness of that statement?
About which one?
It being warm in here.
It is warm in here. Look, I can turn this fan on. That will help everyone, right? I mean, the air is running. Did you hear it just turn on? Do we want it to rotate so it's not just, or would that be more annoying? I am a person who hates air blowing directly on me. So, is this okay for everyone? All right.
Technically, that's false because if x and y are both 1, then they equal each other.
There's a surreal. That doesn't work though. Is there a real number x where for all real numbers y, it's squared can't be that? Yeah, I guess any negative number. No, x is positive. No, I don't think that's true then. I think that the original statement is true. You get that one or the other has to be, right? A statement or its negation has to be true. Okay. Number 4, there exists a married person X such that for all married people Y, X is married to Y. I'm going to write it in words. For all married people X, there is a Y where X is not married to Y. I got more uncomfortable as I went there. Did y'all notice that? Okay. Good to go? Yes? Are we? That's annoying. Sorry. The board rocking back and forth, or the screen. The board's not moving. Okay. My son's in a phase of his life where he was correcting me on that, so it's really fun. All right. Give me a minute. 1, 2, 3. That's what he does to me. I say, give me a minute, bud. And he'll count. Before I lose my patience with him, no. Would he if I let him? 100%. Okay, let's translate these into English, assuming X and Y are real numbers. Number 1. Good. The next one, for all real numbers X and Y, if X and Y are non-negative, then X times Y is non-negative. It feels like perhaps we should have done these in the other order, huh? Y'all think I should change that for the next time I do these notes? These two sets should be in the other order, don't you think? We should practice writing the sentences before we start negating them. Yes? I will swap these. It's the kind of thing when you're editing a code item and like looking at a PDF and reading, you just miss things like that don't flow right. This is why we're here though, so y'all can help me be a better teacher next semester. Wow, y'all, I'm just joking. I want to do the best I can for you. Okay, for all real numbers X and Y, there exists a real Z where X times Y equals Z. Okay. Number 9, we are negating again, just symbolically though. So just doing the negation for number 9 would be there exists an X for all Y. There exists an X such that for all Y there exists a Z where T of X, Y, Z is not true. That is gross looking, but are you following what I did? Changed all the quantifiers to the other quantifier and then negated the statement itself. What about for number 10? What would that look like? I was doing what you told me to do, Janai. What's next?
And not
Good. We got the hang of all of that? Yes? Y'all ready to start writing proofs, aren't you? Can we please stop writing these symbols? Yes. I wish. Okay. I would like to cut about half of those. Does that seem good to you? Or do we need that much practice? Well, yeah. We did struggle with those. Okay, 3.4. 3.4. These are now, we're going to do arguments with those kinds of statements. We're building up to the point where we can finally write a proof, okay? So, here is a line from an argument. Since all integers are divisible by 1, we can conclude that 4 is divisible by 1. This is an example of universal instantiation, which if you say it's true for all elements, then you can say it's true for a specific element. Okay, so universal modus ponens is this thing. Now this looks weird because now these look like, they still look like functions. They're predicates still, but we have this, they're quantified now, so for all x, it's p of x and q of x. So this is some general statement. And then the next line of this argument, this is premise 1, premise 2 of an argument. Y'all with me? Premise 2 is that, well, p of x is true for this particular thing. And so then the conclusion is that q of x is true for that particular thing. So remember, modus ponens looks like this, that p implies q and p, therefore q, right? So this is that same thing. It's just that this is stated in general, and then this is the particular case, a particular case where it happens. Here's an example of that. So if an integer is even, then its square is even. K is a particular integer that is even, therefore k squared is even. So our predicate here, or open sentence or whatever, we could call that E of x, is that x is even. So this would be something like E of x implies that E of x squared. This is saying that k is an even integer, and then the argument is that, okay, well, therefore k squared is even. So this is modus ponens. We okay with that much? Yes? Alrighty. You also have modus tollens. So if we have for all x, if p of x, then q of x, generally speaking, and then not q of a for some particular a, then not p of a. So again, this thing looks like this, modus tollens. P implies q, it's using the contrapositive. Well, that looked like a q. So P implies Q and not Q, therefore not P. That's because the contrapositive is equivalent to the conditional. Okay, so we're going to rewrite this one in the same. I was going to spoil it for you. we're going to write this one and decide if it's valid. Okay? Okay. Every computer science major takes discrete. Andrew is not taking discrete. Therefore, Andrew is not a computer science major. So if we wanted to assign predicates and things here, I'm going to go with this, that C of S means that student S is a computer science major. Let's go with D of S is that S is taking discrete. Okay, so symbolically this argument is that for all students, if that student is a computer science major, then that student will take discrete. Everybody with me on premise 1 of that argument? For all computer science majors, they're going to take discrete. For all students, if they're computer science, they have to take discrete. Andrew, he is not taking discrete. That's a no to that one. And then the argument or the conclusion of our argument here is that therefore Andrew is not a computer. I can't draw C's in parentheses next to one another. There we go. Andrew is not a computer science major. How do you feel about this argument form? You are for it? Yes. This is modus tollens, yeah? Right? This is valid. It's modus tollens at play here. Universal modus tollens. Okay. So what we're going to do right now is we have 5 examples where we are going to decide if the argument form is valid or not, and we're going to talk about why it is or is not. We good? Do y'all want to try some without me? No. Please don't make us. Okay. So our first practice problem we have, all students in this class understand logic. Matt is a student in this class, therefore Matt understands logic. We're going to walk through this. We're going to put it in symbols. We're going to go from there. So that first sentence, let's give like domain and predicates and things here. So S is going to be students in this class, or S is just students. That's our domain. Let's go with D of S. Is that student S is in discrete or in this class? L would be that student understands logic. Y'all good? See what we're doing or no? Yes or no? Yes. Okay. So how do I write this argument form? What does it look like? For all S, this is an if-then statement. If the student is in this class, then they understand logic. That's that first, this is premise 1. Whoa. I didn't mean to really cross through that, but. Okay, so for all students, if a student is in this class, then they understand logic. Okay, that's premise 1. What's that second sentence, premise 2? Matt is a particular student in this class, so we'll call that D of M for Matt. That's premise 2. And then the conclusion, LM. Do you think that this argument form is valid or not? Yes. Why? It is modus ponens. Oh, this is strange. All parrots like fruit. My bird is not a parrot. Therefore, my pet bird does not like fruit. So now I think our domain would be B for birds. Can we go with P of B? Is that the bird is a parrot? And then F of B would that be that bird likes fruit? It's kind of weird, right? Because you've got this sort of like hidden thing happening with the birds in that first sentence. So the first sentence is a conditional statement. What is the conditional statement? If it's a parrot, it likes fruit. Yeah. So for all birds, if it's a parrot, then that parrot likes fruit. That bird, sorry. If it's a parrot, B, if B is a parrot, then B likes fruit. My pet bird, so we'll go with E for that, is not a parrot. So not P, E for my bird. Therefore, my pet bird does not like fruit. Is this a valid argument form or not a valid argument form? Does this make sense? Well, let's think about it. All parrots like fruit. Well, my bird's not a parrot, so it doesn't like fruit. Huh? Like, all students like cookout. Well, my dad's not a student, so he doesn't like cookout. That doesn't make sense, right? My dad can like cookout still, even though he's not a student, right? My bird likes fruit too, even though it's not a parrot. I would never have a bird. I think birds are weird. But, because they are, Emily, in case you were wondering. Okay, so this is not valid. This is not valid for a particular reason. What is that reason? Yes, right. Because that would be the contrapositive, right? That's like, this is the conditional, right? This is the conditional equivalent to the contrapositive, right? What is this? Yes, that is the inverse. So this is saying that the conditional and the inverse are equivalent to one another, and they're not. So this is what's called an inverse error. Those mathematicians being really creative. So the mistake here is assuming that the inverse and the conditional mean the same thing, and they don't. And so that's called an inverse error. All right, number 3. I'm not going to list all these things because I'm not going to do this. Sorry, I'm not going to do this thing right now because these are pretty straightforward. Okay. N is a real number with n greater than 2, then n squared is greater than 4. Suppose that n is less than or equal to 2, then n squared is less than or equal to 4. Let's put this in our logical form, like in this sort of argument structure, and then we'll talk about whether or not it is valid. So n being greater than 2 implies that n squared is greater than 4. This is for all n. That is premise number 1. What is premise number 2? Yeah, or that means that n is not greater than 2, right? So this would be that n is not greater than 2. And you got a big then n squared is not greater than 4. So if n is greater than 2, then n squared is greater than 4. Suppose that n is less than or equal to 2, then n squared is less than or equal to 4. What has happened now? The same thing. Y'all see that? This is P, Q. This is not P. This is not Q. This is an inverse error again. Negating the statements in the same order does not work. Right? That's what happened again. It doesn't work. Okay, number 4. If n is a real number such that n is greater than 1, then n squared is greater than 1. Suppose that n squared is greater than 1, then n is greater than 1. So n is greater than 1 implies that n squared is greater than 1. And we have that n squared is greater than 1. Therefore, n is greater than 1. And that's not good. Why? Is P implies Q equivalent to Q implies P? It is a converse error. That's the converse, right? That's the mistake, is assuming that the converse is equivalent to the conditional, and it isn't. Sounds like he's still going. Did you just peace out? He's still talking.
Yeah, but
Yeah. He's still. I can still hear him
oh,
talking.
it's like back to back, like the classes.
Yeah. He has back-to-back classes?
No, like the classroom. So
Oh.
or is it right there?
Oh yeah.
Okay.
109.
Yeah.
Mhm.
Now you don't think about it.
Yeah. I also know it's him because he's the only one who writes on the board
Oh, yeah.
consistently. So it's like. Okay, if n is a real number such that n is greater than 3, then n squared is greater than 9. Suppose that n squared is less than or equal to 9, then n is less than or equal to 3. So for all real numbers n greater than 3 implies that n squared is greater than 9. Everybody good with premise 1? What is premise 2? Yeah, n squared is not greater than 9 because it's less than or equal to, right? Those are 9s, not q's. I understand that they do look very similar. I don't know how to make my 9s not look like q's. This is how. Now they look like g's. No one's going to be happy with that. I'm not. Janaya, just ignore them. They're 9s, okay? All right, what's the big conclusion? Good. What do we know about this? This is valid. Ooh. This is valid. Because we have P implies Q, and then we have not Q, right? Implies not P. So this is modus tollens. What do y'all think? We got this, right? It's good. I think this is like, I don't know, 3 of your 10 homework questions. Yeah, like, you got this. It'll be fine. I've lost your homework now, so it's in the middle of this. Yeah, Brian, this is where you make an appearance on here. And negations, converse, negations. Oh, yeah. Y'all can do this whole homework now. Friday it is. I stand by the dates we talked about earlier. You're going to start at the beginning of their recording, and I wrote them down because I'd forget. There they are. Okay. So we have gotten through page 19, folks, and we're ready to start 4.1. Yay! 4.1 is really just proving with counterexamples. So we're going to, or with examples. So we're going to do that. And then 4.2 is when we'll start like actually writing proofs. But the book has changed. That used to all be in 4.1. So my notes are kind of mixed together too. Like they added 4.2, whatever. Anyway, I tried to separate them in my notes, but we'll go from here. So page 20. Consider the proposition for every real number x. If x equals 4, then x squared equals 16. Can we prove this? Yes, how? Look, 4 times 4 is 16. Way to go, us. Yeah, or that. You can do that, or you can write 4 squared. Yeah. Okay, did you consider the truth of this implication for numbers that are not equal to 4? Why? Yeah, we did not. Because we get to assume.
I'm too lazy to check every single number.
Fair. Okay, so we need some definitions to work with because we want things other than like x equals a particular number to be the thing that we get to work with. So 2 definitions we're going to start with, and then we'll add 2 more in just a minute. Is the first one is that an integer n is even if it can be written as 2 times an integer. That's what the n equals 2k for some k and z. An integer is odd if you can write it as 2 times an integer plus 1. That plus 1 is important, not minus 1. Got it? So this is the definition of a number being even or number being odd. Soon we will actually prove that all integers are either even or odd, but not yet. Okay, so we want to answer these questions. Is it true? And then how do we justify that 0 is an even number? Can we write 0 as 2 times an integer? This one is weird. But yes, what? 2 times 0, yeah. So 0 is equal to 2 times 0. 0 is an integer, so 0 is even. It's weird to use the number as the integer, but whatever. This is an element, and this is a Blackboard bolded Z, Janelle. I don't know why you would have trouble with that, but look, that looks very fancy. Look, I typed it. Okay. How about negative 301? Is that odd? And then you need to justify it for me. Yes. Yeah, and negative 151 is in fact an integer, so we're good to go. If a and b are integers, is 6a squared times b even? Can you write that as 2 times an integer?
2 times 3 is 4.
So we get to assume this, that the integers are closed under addition and therefore subtraction and multiplication, but not division. So like multiply, this is all multiplication, just addition, whatever. But the fact that you started with 2 integers and you did stuff to them, combine them with multiplication and addition, your result will still be an integer. So we're good to go. That's what it means to be closed under those operations, that you can do that operation and it stays within that set. Okay, if a and b are integers, is 10a plus 8b plus 1 odd? Yes. How do we know?
2 times 5a plus 4b.
And that 5a plus 4b, again, is an integer because the integers are closed under addition and multiplication.
So if it was something like 10a plus 8b minus 2, you could simply add in there, correct?
If that was in here, yes. But if that was like out, you need to be careful about how you do it because that a and the b didn't have a factor of 2 sitting with them. But yes, doesn't matter, as long as a and b are integers and you can pull a 2 out and rewrite it in a way that fits this, then you're fine.
Yeah.
Yeah.
Oh,
Okay, so again, we will assume for now that all integers are either even or odd. We'll prove it in, I don't know, in a week or 2. We have another definition, well, 2 here. N is some integer that's greater than 1. It's prime if for all factors. Those factors are between 1 and n. There are a lot of words there to express that, but if you have some positive integer, some integer bigger than 1 that you can write as 2 factors, those factors are either 1 or n. And if it's not prime, then the number is called composite. Good? Okay. So is 1 a prime number?
yes.
Why? Yeah, and 1 is not greater than 1, so no. That's the first part of the definition there, right? So n is an integer, n bigger than 1, then n is prime if. So it needs to be bigger than 1, so it's not greater than 1. You probably have. Is every integer greater than 1 either prime or composite? Yes, it's either prime or not prime. That was the definition of composite. I almost wrote down not composite, not helpful. Okay, help me write the first 6 prime numbers. Don't start with 1. Oh, okay, and then the first 6 composite numbers.
4, 6, 8,
9,
9,
10. We're going to leave those where we can see them while we read our next bit, or I'm going to leave them where you can see them. You got to turn your page. Sorry about that. I forgot what? Oh, that's only 5. My bad. 6. Read, people. I got it. Sorry, Jacob. Yes. I was listening to you. No. Okay, so to prove there exists statement, you need to find an example, right? That there exists says that there is at least one red car or whatever. So you need to find a red car and point at it, right? I don't know. Is there? Yes. Okay, so to disprove a for all statement, you only need to find one value where it's not true. All cars are red. And you would prove me wrong by pointing to that gray car or white car, right? So that's called a counterexample. Remember that. So to prove a there exists, you find an example. To disprove a for all, you find a counterexample, right? An example where it's not true. Okay. How do we prove this statement? There exists an even integer n. Oops, I told you I was going to leave this up where you could see it. There exists an even integer n that can be written in two ways as a sum of two prime numbers. So a lot to parse there. There is an even integer n that can be written in two different ways as the sum of two prime numbers. In logical symbols, this would be something like there exists an n in 2z. Remember, we're going with 2z as the evens. Do we remember this? I don't know. Have I just done this to myself, or have we talked about it? We have? Okay. So there is an n in 2z that can be written in two ways as the sum of two prime numbers. Okay, so there exists an n in 2z where, I don't know, a plus b is equal to n and c plus d is equal to n, where a, b, c, and d are prime. Ah. What? You could not do this in this order. You could say there exists an n in 2z and prime numbers a, b, c, and d where a plus b equals n and c plus d equals n. Yeah?
The numbers have to be different from each other? Like, can C and D be the same?
C and D can be the same, or like B and D, or B and C, right? Like you don't want the same pair. Yeah. When is such a statement true? Huh? 10 was your number. When you can find one, right? When you can find an n that works. You're ready to do the next bullet point, Brian. What two different things are you adding to get to 10? Did you say 10?
3 plus 7 and 5 plus 5.
No. Nice.
Why I was asking about that.
I went to 16, Lane. I did 5 and 11 and 3 and 13. 10 is good. I like the sneaky 5, 5 there. 3 plus 7, which is equal to 5 plus 5. 3, 7, and 5 are all prime. I'm concerned at the speed with which we're moving. Are y'all lost? Not yet. How positive. Okay, well, guess we'll just keep going then. This might be the only time I'm ready for the test before the test date. It's y'all, it's not me. Or it could be the new notes. Maybe it's better. Or maybe it's worse. We'll find out after you take your test, won't we? You won't fail. Okay. We're going to disprove these statements by finding a counterexample. So it's important to notice that that's what we're doing. We are disproving these statements. So this first one we have, for all real numbers a and b, if a squared equals b squared, then a equals b. What is the negation of this statement? Real numbers a and b, where what's true?
If A squared is B squared.
No, no, no.
A squared equals B squared and A does not equal B.
Yeah, y'all know why I was yelling at you, right? Because you were using the word if again. It's not the first time, Eunice. I didn't yell at them the first time it happened. Oh, I don't think I did. So one of these has to be true, either the statement or its negation, right? So if we can prove the negation is true, we have disproven the original. You with me? Also, we've given a counterexample to the original. So if there exists a pair of real numbers where their square is the same, but the numbers are not the same, then we have done the thing. So give me that example. To the original statement or an example for the negation, but we're going to consider which say a equal to 2 and b equal to -2. You're going to say something like, notice, I'm doing some things right now we haven't really talked about, but I will later. Notice that 2 squared equals -2 squared, and 2 does not equal -2. Okay. Number 2, we have for all real numbers a and b, if a is less than b, then a squared is less than b squared. To disprove this, what would you prove?
There exists an example.
Yeah, there exists a counterexample, or there exists a, b in R, where what?
A is less than B,
Good.
and A squared is greater than or equal to B squared.
Nice.
I think we need a div somewhere in there.
No. Okay. To disprove, we're going to prove that there exists some real numbers a and b, where a is less than b, and a squared is greater than b squared. We can do this, right? I'm going to say something like, consider a equal to, I don't know, -3, and b equal to, let's go with 1. Notice a is less than b. However, I am writing full sentences. Y'all see this? Notice a is less than b. However, oh my gosh, well, not anymore. However, a squared is not less than b squared, since, I don't like how I've organized this. -3 squared is 9, and 1 squared is 1. I'm going to rewrite this. Sorry. I don't like it. It's bothering me. However, a squared equals -3 squared, which equals 9, and b squared equals 1 squared, which is 1. For notice, 9 is not less than 1. Good. We feel good about that one? I do now. I feel better now about it. She's ready to do some pre-calculus. Me too. We good? I'm not going to make us keep going right now. I mean, I'm going to make us eventually. But I'm not going to start this new section with 7 minutes to go. Yeah, we've done a lot today. Y'all got to let that sink in, process. Yeah? This might be the only time I've ever let you go early. Enjoy it. I will give you your homework back when I see you again. And you're going to either bring me homework or email me homework Friday. Yeah? Okay. Have a great rest of your week. Weird that I won't see you till Friday. I could. I didn't know if that was just an accessory you go with all the time, but.
No, I laugh.
Okay. Yeah, are you not supposed to wear pants to lab?
Probably.
I love the conversation about the power percent.
On here?